Hello and welcome to another PlayBASIC code review. My name is Kevin Piccone. I'm the developer of PlayBASIC, and I wanted to show an idea about how you can do sprite masking in a manual sense. Let's have a look at the concept. Open up PlayBASIC down here. It's already open. I wrote this example earlier. I just wanted to go through the code a little bit and give you a sense of what this is actually doing. We'll run the game we'll run the demo. It's not a game. You'll notice that ships are being occluded by the foreground. And I can move the ships forward in front of or behind those planes. Now, when we take a look at the code, you'll notice that the ships are drawn at the end of the process. So normally, when you draw graphics, of course, you draw something and then you paint. We're using Painter's algorithm. We're drawing the backdrop and then drawing the foreground and then the hard stuff in front of it. And the order of those things determines the order of what you can see. So if we draw our ships at the end of that process, it shouldn't be possible for them to appear as if they're going behind things. And that's what we're using this masking idea for. It's quite a common idea. It's not a new thing. It's a kind of an old concept. So what does the program do? It first loads, gets the pathway to a graphic that I know the location of, which is in the PlayBASIC help files. So I don't have to supply you with a graphic. I can just give you the code as is, and you could cut and paste that, and it should run, provided that piece of media is in your help files. It should be. It may not be if you've got a really old version of PlayBASIC. If your version is the current learning edition or a current retail edition, then you should be fine. Once we've got the location of that, we load this ship graphic, we scale it up, we make it twice the size. And then I do something interesting here, is I make a secondary FX image, in other words, an image that's stored in system memory, the same dimensions as the ship image. Whoa. Sorry, that should be... I did change the names of the variables earlier and forgot to change those ones there. Just run it again and see if we haven't broken anything. That's fine. It's okay. Right, so this mask image is just a blank image, nothing on it, and it's the same size of our image ship. That completes the loading of the media process. Then we set up a very simple structure to hold our rectangles, which in this case they simulate a background of some type. I'm just setting a global variable of 50, so we have 50 rectangles in this scene. We set up an array, so each element or index in the array is going to have this structure in it. We run through and randomly create these backdrop rectangles. So we've got a random position on screen across the x-axis, and the width, or its right-hand component of the rectangle is just created by going, give me the left-hand x plus a random value of up to 100. For the y positions, we don't really care. We just give a couple. The theory is there, I wanted to have if you just go completely crazy with randoms, you end up with rectangles that fill the entire screen, and it's not very useful for the demonstration because pretty much they'll just cover everything. And we're also giving each rectangle a depth. Now I'm drawing these things using painters, so to draw the scene, we're going through and drawing all the rects with the lowest depth first, then so any depths of 0, then any depths of 1, and then any depths of 2, and so on. So it's not a very efficient way of doing this particular thing, but it's just there for demonstration purposes. Alright, so we've created our rectangles. We're going to create a list of colors that apply to each depth of rectangle. So any rectangle that's on a depth of 5 will have whatever is in the depth palette. which will be a random RGB color. Again, just for demonstration purposes. The main loop, we've got our main do loop structure, which means at the end of that, we've got a loop. So PB will see the start of the do loop block, and we'll keep rolling down here until it hits the loop, and then this one here has an expression after it, so it's acting as if it's a repeat until statement, really, because you have expressions after these optionally. So this will loop until a scan key or any key in the keyboard is pressed, and then it will just eject out of that and run down to the bottom of the program. In this case, there's nothing at the end, so it will conclude. Inside the loop is what's keeping the game or the demo running. We've got first we're clearing the screen to black, which is RGB 000, that's color black. You might also see this in programs written like this, CLS 0, because RGB equates to an integer value of 0. So some people will shortcut that. Or you might, let's say we wanted white, and we could use a hex value there. That would give us a value of white. Or we could do this to get white. They're functionally the same, and so is this, by the way. -1. And to understand why -1 is the equivalent, you'd have to really dig into how integer numbers work and signed integer numbers work. But this will give you a hex value of actually, in hex, -1 is actually this. And since it's going to use the bottom 6 digits there, which is going to be, each pair is going to be an R. The R, which is going to be this section here. That's the R, that's the G, that's the B. That would be alpha channel if we had any, but we don't. Alright, so we're clearing our screen to black, and we're running through and we're drawing all the rectangles up front. So we're starting from a depth of 0, we're running through and looking for anything of that particular depth. Running through all the rectangles, and if this rectangle happens to be of the same depth, we draw it in the current ink color for this batch of rectangles. And we keep doing that until we're done. So we've drawn all the rectangles. Now we're going to draw the sprites. Now I've just grabbed the mouse position here. Read mouse position. Gives us the X and the Y coordinate of the mouse. I'm positioning, or I'm drawing an image using our original image ship image, which is the silver ship at this location where the mouse is. It's going to position the ship. When we draw it, we're drawing from the top left-hand corner of the image. I'm telling you to draw it transparently as well. So any area of that image that is color 0 or RGB 000 will be screened out of the image, and any other color will be passed through and drawn. That's the main ship, but the orbiting ships are not drawn like that. Mask images. Yeah, whatever. So I'm just running through a 360 degrees set of angles at 30 degrees, grabbing an angle here and computing a position around the mouse position that's 200 pixels away from this location. So if you're familiar with polar coordinates, we've got an angle and a length. That's all we really need, and we've got the base position is where the mouse position is. So we're computing this offset in any direction from that point. It's very useful. Trigonometry is really useful for 2D game development in particular. So well worth having a refresher of that. Then we call our draw masked image, and we're passing it a few different things. We're passing it the original ship, our mask image, which is this secondary image that's the same size as the original ship image, plus the extra information we need to draw this thing when we're done with it. We need its coordinates on screen, and we want it to be drawn transparent at the end of the process. But we also want to know what level we should clip this sprite against, or this image against these rectangles at the top there. So what I mean by that is that when the sprite has a depth of 0, it will be drawn in front of the back layer of rectangles, but behind all the other layers of rectangles that are in front of that. If it was drawn at like layer 20, it would be drawn, there would be 20 layers of rectangles behind it, and then any other layer that was in front of that, it would be clipped against. Hope that makes sense. So let's have a look at the function. This is the only part of the code that's actually showing the concept, right? So when we call this function to draw a masked version of the image, we're grabbing the original surface, the current drawing surface, which in this case will be the screen generally, but it's good practice to get used to asking PlayBASIC what the current surface is, because I know I'm going to modify this inside my loop. I don't want to have a situation where if I call my function, it changes the current drawing surface to someplace unrelated when I return. I want to make sure I restore any changes I make inside the function, I restore them at the end of the function. So for the user's perspective, it just feels like a built-in command. So we grab the current surface, we look at the image that was passed in, which is going to be the original ship image in this case, grab its width and height, then we copy the pixels from this source image to our temporary mask, because we're going to damage this image. We're going to actually write transparent data over the top of the image, so we need to preserve the original image and copy this other one some other place, so we can mutilate it any way we like, and we have to worry about anything else about damaging the original. So this makes a copy of that source image, gets copied across onto the mask, copying the top left hand coordinates and its width across onto the mask at the top left hand coordinates. Next we compute in screen space where our image is would be on screen, because the rectangle coordinates we're going to be clipping against, they're all in screen space. So when we run this again, its coordinates for each rectangle here, let's say, is in this screen space in here, whereas our images, we need to know where that mouse coordinate is, where it's drawing the sprite, and then work out the little rectangle where the sprite's going to be overlapping, if you get what I mean. Once we've got the global position, now we need to do the masking. So we're switching rendering across to our mask version of the image, which is the one we're happy to manipulate and destroy the pixels on. We're going to loop through all of the rectangles we have. We're going to check our clipping depth against the depth of each rectangle. So anything that's actually that has a higher depth, in other words, is a layer closer to us, we want to apply the clipping to. Now we may or may not be impacted by it. The rectangle might be off to the left of us, or it might be off to the right or above. That's all we need to know. It's our position in screen space, so we can clip the two things to each other. Actually, I'm not clipping them, I'm just drawing them over each other. If our current depth is lower than the rectangle we're looking at the moment, we go, okay, we might have to mask this rectangle against our ship to destroy those pixels, so it makes it appear like it's behind it. So we grab its coordinates, it's left and right. We ensure that they are left to right. So x1 is going to be the one on the left of the screen, and x2 would be on the right. So if you had a rectangle like there, for example, x1 would be this side and x2 would be over on this side here. we do a comparison against just this on the x-axis alone. We just compare that against the axis up here that we computed earlier, where the image would be if it was in screen space. If we get an overlap, we fall through and we do the same thing for the y-axis. So we're checking to see if our sprite is in the same shared area on the x-axis, and then we're doing the same thing against the y-axis. If both of those tests meet, then the two rectangles overlap. So we'll grab the top of the rectangle, the bottom, just make sure they're in the order we expect. Do the same comparisons against our source image in screen space. Once we get here, we know the two areas are impacting each other, they're over each other, and now we have to work out how much of the mask, the sprite mask, that we need to draw the rectangle over. And the easiest way to do that is convert the rectangle from screen space coordinates into localizing its coordinates to the image. And all we need to do is compute the width and height of the rectangle, which is what that's doing. And then we subtract the rectangle's top left-hand coordinate, and we take away the image's screen space top left-hand coordinate, and that gives us the offset. Then we can draw this rectangle onto that surface, and it will effectively because it's been drawn in RGB color 0, and the image we know has a transparent color of RGB color 0. If I draw that over the top, it's like making those pixels transparent. And that's the whole process. Now you might think, well, it's a pretty manhandly kind of solution to try and do this. But what it does mean is you could have a pre-drawn scene, a very elaborate scene really, it wouldn't matter, and then have a list of these clipping planes that you apply in post. So if the background picture is drawn as a painting or a picture, and you need something to move behind something else, like you would see in one of those games like Monkey Island and those kind of point and click games, where the artist is out there drawing a nice image, and then you might have to make the character walk through the scene as if it was inside it, even though it's drawn afterwards. So you would do that by having masks. Here I'm using rectangles, but you could use any kind of shape actually, polygons, other images that happen to be in black, and use the same principle to draw those pixels, those black pixels over the top of to nullify or to be drawn as mask color onto the target. So when they're drawn at the very end, they just appear as transparent pixels. Okay, so let's recap again. We're going through all the rectangles in the scene. We're checking if there's an overlap on the x-axis. Do they share a region on the x-axis? If they do, we move to the y-axis. Do they still overlap? If they overlap on the x-axis and they overlap on the y, then they must be impacting. We localize the coordinates. First we compute the width and height of the rectangle. Then we compute the top left-hand coordinate local to where the image is, because we're drawing to the image, we're not drawing to the screen here, we're drawing to the image, which is going to be, now we're drawing an image pixel space. So pixel 00 is actually going to be, when it's rendered out to the screen, it's going to be on screen at wherever this image x1 is. But we need to subtract the two from each other to get the offset relative to the image. I hope that makes sense. Once we have it, we can draw we can nullify the pixels from that image, and then we're right. We restore rendering back to the old surface, and we draw the sprite draw the image at its location, but with this time we don't draw the passed in original image, we draw the mask image. And just to demonstrate this actually is doing that, if I put a just a request on mouse button there, if this equals 1, right? So it'll be transparent when mouse button is 1 and solid when they're not. So when we draw the images as they really are, we can see that the areas around the pixels that are occluded by rectangles are being nullified, they're being rendered over. If I push the mouse button and draw them as transparent sprites, now it appears as if they're going behind, but they're not really. I think if you're going to implement this, make a more robust version of this solution, you would store your sprites, each would have their own separate mask rather than share the mask throughout the whole set. That way, when you're doing animation, you could copy from your bank of animation frames into the mask and then apply any occlusion that's necessary, and only apply it if it's actually going to be drawn to screen. Here, we're not even checking that. Like if I move the sprites off screen, we're still applying the same masking process. What we should do is we should check does this sprite even need to be drawn? But we're not. This is just a demonstration. Hold the mouse button down to apply our occlusion. The sprite in the middle won't, because it's drawn just with normal draw image. It'll always appear in front because it was drawn last. Even though the ones around it, they're actually drawn after that sprite's been drawn. The one in the middle I'm talking about. All right. Hope that was helpful. Hopefully it gives you some ideas about how you might tackle doing completely different types of games that you might think would be too challenging to make. They're probably not. Enjoy that. Thanks for watching, and I'll see you next time. Bye. Thanks for watching, and if you want more programming content, please subscribe to playbasic.com.